In this next section, we want to look at ionic bonds. So as a quick review about bonding in general, in a chemical bond, the valence electrons, those outermost electrons, the electrons in the highest energy level of the atom, are transferred from one orbital of one atom to the outer orbital of another atom, or shared among those orbitals. In an ionic bond, we're looking at cases where an electron is transferred from the outer orbital of the element with a low ionization energy to the outer orbital of the element with a high ionization energy. Generally, the metal loses the electrons and the nonmetal gains the electrons. Now, when we're putting compounds together, we're looking at something called the octet rule. If you remember, with valence electrons, the maximum number of valence electrons that can occur in an atom is 8. So in stable compounds, you're going to have the same electron configuration as a noble gas, and a noble gas has 8 valence electrons. So we refer to this as the octet rule, the rule of 8, or octet being 8. So we're looking to have 8 valence electrons around any atom to make it stable. Now when we have an ionically bonded compound, we get a lattice structure, or a solid structure in most cases when it's a solid, and not separated like it would be if it was dissolved in water. We, for example, here have lithium and fluorine. Now normally, lithium is a larger atom than fluorine, but when it loses an electron from its outermost energy level, now it only has 2 electrons, both in the first energy level. Fluorine has gained an electron in the second energy level. So fluorine actually has gotten larger, lithium has gotten smaller. We can see from the various anions and cations that the size dramatically changes when we form anions and cations. If we lose an electron, we generally lose the entire outer energy level of an atom, and so we go to a lower energy level, which makes it significantly smaller. And when we gain electrons, we're gaining electrons without gaining protons into that highest energy level, so the atom gets larger. Now, when we have an ionic bond, we actually refer to that as a formula unit, not a molecule. The individual ions, or polyatomic ions, are held together to form an individual unit. However, if you look back at the picture we were looking at earlier, you see that we don't just form one lithium with one fluorine. Positive lithiums are attracted to negative fluorines, and we get a structure where we have lots of lithiums and lots of fluorines. But it all just depends on the size of the solid that we are working with. So it really depends on what's happening with the structure. So that's why we go by the formula unit. The formula unit for that compound there was LiF. You can think of that like a molecule, but in reality, when you have LiFs together, you'll get lots of Li's and lots of F's. So it's not like a true molecule where you just are holding 2 atoms together and they're separate from everything else. If you have polyatomic ions, the polyatomic ion atoms are held together by covalent bonds, and then as a unit, they bond ionically with the anion or cation. Now, whenever we're looking at structures, we use something called electron dot structures. Electron dot structures were developed by G.N. Lewis in 1916. They're also commonly referred to as Lewis dot structures. In the Lewis dot structure, the element symbol is used to represent the nucleus and the inner orbital electrons, and then dots are used to show the valence electrons. So if we go across one of the rows, let's say the third row, the third energy level, you have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Aluminum has 1 valence electron, so we'll put 1 dot with aluminum. Magnesium has 2. Aluminum has 3. Silicon, you can put the first two together on one side because you can think of that as one of the orbitals, the 1s, or the 3s, or you can separate them out and have 3 on one side each. Phosphorus has 5 valence electrons. So just like orbitals, if you've got the symbol, you've got 4 sides where you can put dots representing the s orbitals and the 3 p orbitals. Sulfur fills up 2 on one side, 2 on another, and 1 on the other 2. Chlorine has 7 valence electrons, and argon has the octet of 8 valence electrons, no more than 2 per side, just like in an orbital can only hold 2 electrons. Now let's look at the case of ionic bonding. In an ionic bonded compound, we're going to look at the electron dot structure. So the electron dot structure here, we have potassium with 1 dot, chlorine, which has 7. To be stable, we want to get each to 8. Now, chlorine can easily get to 8 by gaining 1 electron. To gain 1 electron, it takes it from the low ionization energy, potassium. So we end up with chlorine with 8 dots, and since it has 1 additional electron, it has a charge of -1. Potassium has lost its dots, so it has no dots around it. It is +1. But no dots is really the same thing as 8, because potassium, when it loses its valence electron, becomes just like argon, which has 8 valence electrons. So they're stable, and we write the ionic dot structure like that. AlCl3, you have aluminum with 3, and you have 3 chlorines, each with 7. So 1 aluminum's electron goes to each of the 3 chlorines. We end up with aluminum with no electrons around it, which is the same as having 8, a 3+ charge, and we have 3 chlorine atoms, ions, each with a -1 charge. So we're not actually connecting the molecule together. What's holding the molecule together is the electrostatic attraction of the 2 positively charged aluminum and the negatively charged chlorines. Another one, Ca3N2. So if you think of Ca has 2 dots, there's another Ca that has 2 dots, there's a third Ca that has 2 dots, there's a nitrogen that has 5, another nitrogen that has 5. So we need to fill up, so 2 can go here, 1 from here can go here to fill up that, 1 can go here, and 2 each in the bottom one. So we end up with Ca, 2+, Ca, 2+, N with 8 dots, 3-, N, 3-. We have 1 more, Ca, 2+. Here you can see why the charges are the way they are and why they put together in the atoms that they do. The next thing we'll look at is molecular dot structures, what happens when we have covalently bonded molecules.